Welcome back. We are about to continue on with the Nature of Light worksheet 4B, which we're looking at length contraction and relativistic momentum. In the previous videos, we have done questions 1 through to 5. We're now going to focus in on questions 6 through to 9. So let's have a look at question 6. A muon is travelling at 0.95 c, which is 95% the speed of light, and decays in 4.2 milliseconds. Okay. So let's answer the question. How far would the muon have travelled as measured by an external stationary observer? Okay. So this is the time that we observe it to be decaying, and it's travelling at that. So we're simply going to use, so this is 6a, sort everything out there. So velocity is equal to distance over time, therefore distance would equal velocity times time. So we have a velocity of 0.95 c and a time of 4.2 milliseconds. And this will give us the distance that we would observe this particle to decay in. Because this is what we observe that velocity and we're observing this time. Okay, so we will observe this distance. Rightio, so popping that into our calculator, 0.95 times 3 exponent 8, this definitely is 95% speed light, yep. Multiplied by 4.2 exponent negative 3. We have to use the proper units now. So this is how many meters it would be. It would be 1,197 that many meters. In other words, it would go 197 kilometers, okay, in that time, because it's traveling at a phenomenal speed. Okay. Rightio. So the second question is, how far did the muon travel before it decayed as observed by an observer traveling with the muon? Okay. So the muon will decay in 4.2 seconds. So we're going to apply relativity to all of this. So we have got a gamma factor going on here of with a velocity of 0.95 c. So our gamma factor is 1 minus 0.95 squared, and that will give us 1 over the square root of 1 minus 0.95 squared, so 3.2. Okay, now the time at velocity is equal to gamma time proper. So let's once again use this box here. This is our muon. Our muon is traveling at 0.95 c. So you're traveling with the muon and you see the muon's clock. Okay, you see your time as normal. Okay, we are outside here and we are looking out at this muon as it travels. We measure the time to be 4.2 milliseconds there. Okay. We're also measuring, you would measure the length of everything properly. We are measuring out here a length at velocity. Because remember, we are moving this way. We see, you think you are stationary because you're traveling with the muon here. We see length being contracted. So this here is what we see outside. So this must be the contracted length, okay, because that's what we observe this length here to be, okay. So you, being with the muon, would see a longer length because this is the contracted length, okay. I've just realised I've written the time dilation formula down here. It's actually LV equals L naught on gamma is what we're trying to do here. So we've now worked out this one over here is our L naught. Now, because I'm using this formula here, with my gamma separated from the actual formula, units are preserved. So if I'm doing everything in kilometres, I can just do that in kilometres. So it's 197 kilometres equals L naught, which is what we want, divided by the gamma, which is 3.2. So 1197 divided by 3.2 is equal to 3, oops, not divided to, it's times by that, isn't it? So 1197, let's try again, 97 times 3.2 equals 3,830 kilometres. Okay, so you would travel 3,830 kilometres before you decay. Yeah. Okay. I'm just having a look at my values here. Got that right. I must have rounded this number here. I've got it as something else. Okay, I'll just continue on. And C, finally, says, how long did the muon take to decay as observed by you as an observer here? So TV equals gamma T naught. Remember, we saw this go here at 4.2 milliseconds, and 3.2 is our gamma factor, and let's have a division there. So it is 4.2 divided by 3.2, which is T naught equals 1.3 milliseconds. Okay, which I've got correctly. I've just got the second answer on the worksheet incorrect, unless I've done something stupid here. Okay, so that is question 6. Let's move to question 7. Right, whoops, this paper. Question 7. An electron has a rest mass of that value there. That's negative 31 if you can't read it. Calculate its momentum when it travels at this velocity here. Okay, there's 5 nines over there. Okay, so our momentum, so this is question 7, is given as gamma momentum. So the momentum at a velocity is gamma times the momentum if it's not at velocity there. It's proper momentum. Obviously, it has to be at velocity to have momentum. So this gamma is going to be 1 minus, I said 5 nines, so it's 99999 squared. So this is going to be a huge gamma. How huge, I don't know. 1 over the square root of 1 minus 0.12345 squared, 223.6. It's actually 6.1. Okay, just rounding there. Okay, so its momentum is given by this formula, as I said a few moments. If we were to multiply this out, remember this is actually mv. So gamma is equal to, momentum at velocity is actually gamma mv, where the mass of the particle at times the velocity there. Okay, so this will be 223.61 multiplied by the mass of the electron, which is 9.109 by 10 to the minus 31, multiplied by the velocity of this electron. Now this electron is 0.99999 times the speed of light. Okay, so let's just unpack this expression here. So there is the gamma factor. That's the mass, and this is the velocity. So remember, momentum is just simply mass times velocity, and the relativistic momentum is simply the gamma times the normal momentum. Putting that into our calculator, I'm just using the gamma factor that is left on the screen, multiplied by the mass of the electron, which is given there as 109, exponent negative 31, times 0.12345 times 3 exponent 8. So it is 6.11 by 10 to the minus 20 Newton seconds. Okay, let's just check I've got the right answer. Yay! Okay, let's go to question 8. Now, question 8 says, a small particle has a mass of 0.25 kilograms when stationary. Find its momentum when it's traveling at 90% of the speed of light. Okay, so this is nearly identical to the one above. Okay, so I'll very quickly go through it. The relativistic momentum is equal to gamma times the natural momentum, or so I should say the normal momentum, which is also known as gamma mv. So the gamma factor in this situation for 90% of the speed of light will be given by that formula there. That is 1 over the square root of 1 minus 0.9 squared. So that's 2.29416. It's actually keeps on going. Rightio. So let's now calculate the momentum. So it's 2.29416 times the mass of this object, which is 0.025 kilograms, times the speed that it's traveling. Well, it's 90% of the speed of light, so it's 0.9 times 3 by 10 to the 8th. So there is the velocity. Okay, so here, that's the velocity there. Rightio, multiplying that out, 0.025 times 0.9 times 3 exponent 8, and that gives us 1.549 by 10 to the 6 Newton seconds. Okay, checking that I'm all good for that question. Oh, good. Okay, I've in the actual answers, I've got this in mega, so it's 0.5 mega Newton seconds. So it's just that exponent becomes the capital M there. Okay, now the next question, let's have a look at it. Final one for this video. An electron in motion has a momentum given by this value here. Okay, calculate the velocity at which it is traveling. So there's a difference between this question and the last two, is that I'm given the momentum and I've got to calculate back the velocity. Now this is going to be a little bit more tricky, I think, than these two up here. So let's just see how we go. Let's plug in the values and work it out. So to calculate a velocity, we need to calculate a gamma factor. So let's see what we can do here. So question 9. Okay, we know that the momentum at velocity is equal to the proper momentum times the gamma factor. So this would equal gamma mv. Now I know this value over here is equal to 1.58 by 10 to the minus 20 Newton seconds. Okay, I know this value over here because it's an electron, so I can put that one in. And that's going to be 9.109 by 10 to the minus 31. And then it's going to be gamma V. Okay, so let's work out what gamma V is. Gamma V would be 1.58 exponent negative 20, okay, divided by this value here, which is 9.109 exponent negative 31. Okay, that didn't look very good. Just check I've done the right. Minus 20. Oh, yes, it's okay. It's 10 to the 10 there. Okay. So that's 1.7345. I'm just going to round that by 10 to the power of 10. Okay. Now, does that get us any closer to our answer? We need to find this v, but I can't find this gamma with the information I'm given. So let's now go back to the actual first principles of gamma. Now, gamma is given as 1 over the square root of 1 minus v squared on c squared. That is its proper thing. So this one here, the gamma has v in it, which is the same as this v here. So v times gamma would be v over the square root of 1 minus v squared on c squared, and it would equal this value here. Okay. Now I've got a formula which only has v in it, remembering c is a value that we do know. So we just got to solve for v. So let's just do that now. So the first thing I'm going to do is square both sides. So squaring that answer. Oh, that's nice. Okay, so we get v squared on 1 minus v squared on c squared equals, now the square comes to be that. I am just going to round that to 3.0. Okay, so that's 3.0 by 10 to the 20 values there. Okay, let's bring it to a common denominator. So I'm going to multiply through here by, that's v squared over c squared minus v squared equals, I'll make this c squared, that's it there, equals 3 10 to the 20. That means I can now bring that up to the top. So c squared v squared would equal 3 by 10 to the 20 times c squared minus v squared. I'll just run off the screen. Okay, so that's a stacked fraction. The fraction's got, the denominator's got a denominator, so that denominator comes to the top. So we move from there to there. This gives us c squared v squared up the top here, and I've multiplied this up to that point there. Okay. I need to get all my v squareds together. So c squared v squared would equal 3 by 10 to the 20 c squared minus 3 by 10 to the 20 v squared. Bringing this over, I will get c squared v squared plus 3 by 10 to the 20 v squared equals 3 by 10 to the 20 c squared. Factoring out the v squared, and then finally getting v squared by itself. Okay, now putting that into our calculator. This is going to be interesting. Okay, so let's do that. Let's get the shine off that screen. Okay, so it is 3 exponent 20 times a c, which is 3 exponent 8 all squared. On the bottom is 3 exponent 8 all squared plus 3 exponent 20. And that gives us 8.9973 by 10 to the 16. That was v squared. So v finally is the square root of that number. And that is 2.99955 by 10 to the power of 8 meters per second. And finally, if I divide that by 3 exponent 8, I'll get that to 0.99985 c. There we are. And that is the velocity of that electron. Okay, more complicated than a simple question like that looked, but that's the way those type of questions are done. Okay, this will be the end of this video. The next video will continue on question 10.